All right, so today we are going to finish up Chapter 8. We're going to go back and look at solving rational equations. We did that before the exam last week, and so I'm going to go back and do a little bit of reviewing with solving rational equations. And then we're going to look at some word problems with rational equations. In the textbook, there's a whole bunch of different kinds of word problems. We're only going to look at one kind specifically. And there'll be a couple of those will be in your WebAssign homework from the end of Chapter 8. And then we're going to start in on Chapter 9 and start talking about solving square root expressions. And Chapter 9 is all about roots and radicals, and kind of preparing a little bit for the quadratic formula and solving quadratic equations using the quadratic formula, and some other things with radicals. I want to point out that the Chapter 8 WebAssign homework is due next Monday at midnight. So you have until the 9th to get your Chapter 8 homework done. Most of you did pretty good as far as getting your Chapter 7 homework done on time. And so, try to keep up with the WebAssign homework as best you can. Several people have been pretty consistent about asking me questions on WebAssign, so that's fine, or about WebAssign problems. Let's see. Finally, the last thing I wanted to mention was office hours, and I did send an email out to you guys yesterday, I believe, and so hopefully you got those. I think I sent a couple of emails actually pertaining to your test, and the fact that no matter how you did on exam 1, that the final exam replaces the lowest test grade. So, even if you did not do real well on test 1, the final exam can replace that grade, so it doesn't have to show up on your grade. So now the deal is two things at this point is what I would say is keep up with your WebAssign homework, try to get all that done. Remember that you can go back through and rework problems over and over again until you get them right. So there's no reason why you shouldn't get a 100 on your WebAssign stuff. And and then start concentrating on preparing for exam 2, which is in like 3 weeks. And if you can do well on exams 2 and 3 and the final, and keep up with your WebAssign homework, then you're going to pass the class, regardless of what you did on exam 1. So also, I'm expanding my office hours, and I sent that email out, but I wanted to remind you guys, both you guys that are here with me today, live, and then people who are watching this video later, I've been doing evening office hours twice a week, and so I'm going to 4 days a week on evening office hours. So Monday, Tuesday, Wednesday, Sunday, Monday, Tuesday, and Wednesday I'll be online in the evenings. So take advantage of those hours. I had a couple of people stop by last night for my office hours last night and ask me some questions. So it's just like any regular office hours. Just stop in to my WebEx room, and we can go over some homework or whatever, and we can work on some problems together, and hopefully straighten out some things for you. So kind of keep that in mind. All right, so then today we want to, like I said, we want to finish rational equations, and so I'm going to flip the screen here, and I just want to look at a rational equation or two to kind of go back and review that a little bit one last time in class. And then after that, we're going to get started and do a little bit of word problems, and we'll start it in Chapter 9. Okay, so rational equations. This was section 8.6 in your textbook, and I am looking at problems on page 963 of your textbook, and I'm going to pick off some problems out of there to work. And so I'm looking at problem number 326, which looks like this. This is 2 over, and the book, it uses the letter S. I'm going to use the letter X just because my S's look too much like my 5s, so I don't want to confuse people. So this is our equation, 2 over x plus 7 minus 3 over x minus 3 equals 1. Now remember, to solve a rational equation, first thing is to check for restrictions. So kind of remind you about that. Restrictions are values for the variable that make a denominator equal to 0, right? So the denominators in our problem are x plus 7 and x minus 3. So you set those factors equal to 0. Just look at the denominators, remember, only denominators. And you get x equals negative 7 and x equals 3. And so those are my restrictions. X cannot be negative 7 in this problem, and x cannot be 3, because either one of those would give you a 0 in the denominator. And so I kind of note that at the beginning of the problem, that if when I go through and solve this equation, if I get either of those restrictions, I have to throw that number out of the solution set. All right, so the deal here, remember, is you want to write down the least common denominator, because the idea is we're going to try to get rid of those fractions. And so the least common denominator, we use all the factors that we see in any of the denominators, and that's x plus 7 and x minus 3. And so that so we use both of those factors in the LCD. They're all raised to the first power, and so that's my LCD, just those two factors multiplied together. So now what we're going to do, I'm going to rewrite this problem so that I get a little bit more room here, is we're going to multiply both sides of this equation by the LCD over 1. Remember, that's the deal when you're solving a rational equation. You've got two sides to this equation, and you're going to multiply both sides by the LCD over 1. Because it's an equation, that's allowed, right? Because as long as you're doing the same thing to the left and to the right side of the equation, that's not a problem to do that. So we're multiplying both sides by the LCD over 1. So this is x plus 7 times x minus 3 on this side of the equation over 1. And this is x plus 7 times x minus 3 over 1 on this side of the equation. So on the left side, because there's subtraction over there, this is the distributive property, and you're multiplying both of those fractions by the LCD over 1. And remember, the idea is you're trying to get rid of those fractions when you do this. All right. On the right side of the equation, there is no addition or subtraction, so there's no distributive property over there. All right. So when you multiply through, you have 2 times x plus 7 times x minus 3 over x plus 7 minus 3 times x plus 7 times x minus 3 over x minus 3 equals, and then the other side of the equation, there's no fractions over there, so I just have x plus 7 times x minus 3. All right, so, and remember, I take the time to write that step out. Some students skip that step that I just wrote down and just go ahead and cancel things right away. That's up to you, but I'm going to go ahead now, and I think writing the step out shows you what's going on. So I go through and I cancel out factors, and remember, when you do that, you should be left with an equation that does not have any fractions in it. And sure enough, I don't, right? The first fractions, I'm just left with 2 times x minus 3. Second fraction, I'm just left with 3 times x plus 7. And on the other side of the equation, I just have x plus 7 times x minus 3. So boom, I've got, you remember, this is kind of like a magic trick, and you're trying to make all the fractions disappear. So that's what we've done. We've made all the fractions disappear in this problem. All right, so now what we're going to do is we're going to multiply everything out, see what kind of an equation we have. Remember that we've seen some problems where the equations are linear, and some problems where the equations are quadratic. So you have to see whether you have a linear or quadratic here. So you multiply all this stuff out. You have 2x minus 6. Be careful with the signs on the next one, right? This is a negative 3, so this is negative 3x. And then negative 3 times 7 is minus 21. So notice both signs change there, right? So be really careful with the signs there. That's a negative 3 that you're multiplying through by. Equals, and then on the right side of the equation, I use the FOIL method to multiply that out, and you have x squared minus 3x plus 7x minus 21. And because I have that x squared term in there, I see that this equation is quadratic. And so remember, as soon as you see that it's quadratic, that means you have to set equal to 0, right? You need 0 on one side of the equation. And so go ahead and collect like terms. And what I'm going to do, since the x squared is on the right side, I'm going to get 0 on the left side of the equation. So I collect like terms. You have 2x minus 3x is negative x. And then you have negative 6 and negative 21 is minus 27 equals x squared plus 4x minus 21, like that. All right, and then like I said, I'm going to get 0 on the right side, so I'm going to add x to both sides of the equation, and I'm going to add 27 to both sides of the equation. All right, and so when I do that, I get 0 on the left side, and I have 0 equals x squared plus 5x plus 6. Oops, plus 6. And so I've got that quadratic, because the only method we know for solving quadratics right now is the factoring method. You better be left with something that's factorable. So, check that and make sure that that's what's going on there. This factors, this expression factors x plus 2 times x plus 3. And so you set each factor equal to 0 and solve the equation, each of those equations, and you get negative 2 and negative 3. And now negative 2 and negative 3, neither one of those is a restriction. You always check the restrictions at the end of the problem, but neither of those is a restriction. And so those are my solutions right there. And my solution is negative 2, negative 3. All right, so that's a hopefully reminds you of some things with solving rational equations. So the next problem I want to look at, I'm going to do one more like this, and then that will finish up what we're going to do with these. So I'm going to look at number 328 next. Please stop me, for those of you who are watching live. If you have a question, slow me down, and we will go back over a question that you've got. So number 328, you have w plus 8 over w squared minus 11w plus 28 equals 5 over w minus 7 plus 2 over w minus 4. All right, so on this problem, before you do anything with restrictions or LCD or any of that stuff, first thing you want to do is factor all the denominators. Make sure that all the denominators are factored before you do anything else. So first denominator factors, that's an easy trinomial, and it factors w minus 7 times w minus 4. And then no factoring to do on the right side of the equation. All right, the restrictions in this case should be pretty easy to look at. Because you've got pretty simple factors there. W minus 7 equals 0 and w minus 4 equals 0. So my restrictions are that w can't be 7 and w can't be 4, right? Because when you solve both of those equations, you get 7 and 4 as solutions. So those are numbers that I can't get at the end of the problem. So I have to be careful about that. All right. So now I'm going to go ahead and write this equation down again, just to give myself a little bit more room. And remember, what we're doing is we're going to multiply left side, right side of the equation by the LCD over 1. So I put brackets around both sides of the equation. My LCD in this problem, I use all the factors that I see in the denominators, which is w minus 7 and w minus 4. And so those are the factors I need in the LCD, and I don't need any powers on any of them, and so that's my LCD. So I multiply both sides by w minus 7 times w minus 4 over 1. On the left side of the equation, there's no addition or subtraction. So this is just a matter of canceling factors out over here. The w minus 7's cancel, w minus 4's cancel, and on the left side of the equation, I'm just left with w plus 8. On the right side of the equation, though, I do have the distributive property because that's an addition problem. And so you've got to multiply both factors by that LCD over 1. And if you can cancel stuff out without having to write this step out, then do it. That's fine. But I'm going to go ahead and write this step out, where I multiply both of these fractions by w minus 7 times w minus 4. All right, and then what should happen there? The denominators, sure enough, cancel out, and I'm left with something with no fractions in it. That's my goal. So you get this equation. When you're finished with that step, and you're left with an equation with no fractions in it, yay. I get rid of all the grouping symbols, and I answer the question, what kind of an equation is this? In this case, this is linear. There are no squared terms in there anywhere, and so this is just a linear equation. So I don't want to set this equal to 0. I just want to solve for w, just get w equals something. Right? And so collect like terms. So you get 7w, that's my 5w and my 2w, and then negative 20 and negative 14 is minus 34. And then what I will do here is I'll subtract w from both sides, and that'll get all the w's on the right side of the equation. And then I'll also add 34 to both sides. That'll get all the constants on the other side of the equation. And so you get 42 on this side, on the left side of the equation, equals 6w. And then finally, solve that equation. Just divide both sides by 6, and you get the w is 7. And notice what happened here. Going back to the beginning of the problem, w equals 7 is a restriction. And so 7 is a restricted value. So throw out. And notice that's my only solution in this case was 7, so we're throwing that out. And so the solution set in this case is the empty set. So you either write braces like that, or you write, or you just write no solution in words. One of those two, but you got to tell me at the end on a problem like this that there's no solution to the equation, and those would be the two appropriate ways to do that. It would either be write braces with nothing in the middle, or just write the words no solution in. Okay. All right. So that's a quick rundown. That's stuff we did on the last in the last lecture, but it was a quick kind of review of solving rational equations. And so now what we want to do is look at one kind of application for rational equations, and these are in your textbook, are in section 8.8 of your textbook. And so we're looking at applications, and I'm just going to look at one kind of application. And this is section 8.8, and the type of application is what we call work problems. And so, you know, everybody okay? Yeah, welcome, Nancy. All right, so what we're going to do is look at some work problems, and this is on page 990 in your book. And I'm looking at problem number 448 out of on page 990 of your book. And so I'm going to read the problem and then kind of read it again, and we're going to write down some important information here. The problem goes like this. It says, it takes Sam 4 hours to rake the front lawn while his brother Dave can rake the lawn in 2 hours. How long will it take them to rake the lawn together? Right, that's the question. Sam takes 4 hours to rake the front lawn. Maybe Sam's the younger brother, and his brother Dave can rake the lawn in 2 hours. And then if they go and start working on the lawn together, and provided that Sam and Dave don't fight, how long would it take them to rake the lawn if they're working together? All right, so the problem goes like this. Sam takes 4 hours. Dave takes 2 hours. And then so together, how long does it take them to do the problem if they're or to rake the lawn if they're working together? That's the problem right here. And so the way this is sometimes called a work problem. And the way I approach work problems is like this, is to kind of make a chart here and think about it this way. So if, and we got to answer this question. Before we do the chart, let's answer this question. If Sam takes 4 hours to rake the entire lawn, how much of the lawn, and so as I say how much, I'm talking about a fraction, how much, and we'll write the word fraction there, of the lawn will Sam rake in 1 hour? How much of the lawn would it take him to rake it in 1 hour? Well, if you think about it, if this is the lawn right here, this little box, right, and it takes Sam 4 hours to rake that entire lawn, then in 1 hour, what are you going to do? Wouldn't it make sense that in every hour, Sam would rake the same piece, same size piece, basically. And so 1 hour, what Sam's going to rake is a fourth of the lawn. And he's going to rake a fourth of the lawn every hour. All right, so if you get that idea in your head that if Sam takes 4 hours to do the entire lawn, that it takes him that in 1 hour he does 1/4 of the lawn, which is just the reciprocal of 4, notice, then you could build this little chart that I'm talking about. So what you do is you write the individuals that are involved in the problem. So this would be Sam, Dave, and together. And I tell you what, let me move that over just a little bit. Okay. So how long does it take each one of them? Well, it takes Sam 4 hours. It takes Dave 2 hours. And together is, we don't know. But that's our unknown in the problem, so I might refer to that as X. All right, the next column. What fraction do they rake in 1 hour? So we just talked about this with Sam, that if Sam takes 4 hours to do the entire lawn, that every hour he rakes a fourth of the lawn. That's just the reciprocal of 4. So Dave, it would be the same idea, right? In 1 hour, Dave, well, it takes him 2 hours to do the entire lawn. So in 1 hour, he would do half of the lawn. Again, the reciprocal. So notice it's always the reciprocal. And so then what do we get together? That if it takes them X hours together, then in 1 hour, it'd be 1/X. So those fractions represent what? They represent how much of the lawn each one of them rakes in 1 hour. Sam rakes a fourth of the lawn. Dave rakes half of the lawn. Together they rake 1/X of the lawn in 1 hour. So then you just take advantage of the idea that if you add together what Sam does in 1 hour plus what Dave does in 1 hour, that should equal what they do together in 1 hour. So you get this equation, 1/4 plus 1/2 equals 1 over x. And boom, we have this rational equation that describes this work problem. It actually a relatively simple rational equation. We could solve this by multiplying both sides by the LCD over 1. The LCD in our problem in this case would be 4x, right? Because that's 4 is the least common multiple for 4 and 2. And then we also need the factor x in there. So we would multiply left side of the equation by 4x over 1. We'd multiply the right side of the equation by 4x over 1, like that, to clear the fractions. So this would give me 4x over 4 plus 4x over 2 equals 4x over x when I multiply everything by 4x like that. And notice that all the fractions go away. You end up with x plus 2x equals 4. Add those together, or solve the equation, which is a linear equation. You get 3x equals 4, or x equals 4/3. Now remember what x represents in this problem. X represents how long it takes them to work or to rake the lawn if they're working together. And so that 4/3 implies then that what? It takes Sam and Dave 1 1/3 hours, 4/3 of an hour, 1 1/3 hours to rake the lawn if they work together. Notice that it should be the case that the answer you get is less than the length of time it took each one of them individually to do the lawn, because it makes sense. If you think about it, they should be helping each other. So it should be faster. You know, it took Dave 2 hours to rake the entire lawn. So if Sam's helping him, it should take less than 2 hours. So 4/3 of an hour, or 1 1/3 hours, makes sense. 1/3 of an hour, by the way, is 20 minutes, so it's an hour and 20 minutes it takes them to work to rake the lawn working together like that. All right. All right, so let's look at one more problem like that. You know, that's a pretty straightforward process for work problems. I'm just going to work one more. And this is problem number 458. All right, 458 says it takes Tina 3 hours to frost her holiday cookies, but if Candy helps her, it takes 2 hours. So in other words, if they're working together, it takes 2 hours. How long would it take Candy to frost the holiday cookies by herself? Okay, so it takes Tina 3 hours to frost the holiday cookies. So let's write down that information. Tina takes 3 hours. It says, but if Candy helps her, so notice when it says helps her, it means they're working together. So together, it takes 2 hours. And so then the question, how long would it take Candy to frost the holiday cookies by herself? So Candy takes how long working by herself? All right, that's our question. All right, so you know, you can work this problem exactly. I mean, there's a slight difference in this problem about the way to set up the equation, but because the information is slightly different, but we can do this problem the same way. So we look at Tina and Candy. I like to write out the individuals first, and then working together is the last. Well, if I could spell, that would be good. And working together at the end right here. So it takes Tina 3 hours to frost these cookies. Candy, we don't know how long it takes her, so that's our unknown. And working together is 2 hours, like this. So that's how long it takes each one. So then the next column, the last column, is in 1 hour. How much of the cookies, what fractional part of the cookies do they frost in 1 hour? So this is the reciprocal part, right? This is always going to be a reciprocal here. So this should be 1/3. This should be 1 over x, and this should be 1 over 2. The unknown just kind of appears in a different place in this particular equation. That's the only thing different here. So what do we have? That if you take what fractional part Tina does in 1 hour plus how much Candy does in 1 hour, that should be equal to how much they do together in 1 hour, right? So the individuals added together should be equal to how much they do together in 1 hour. All right, so the least common denominator in this problem, you take the 3 and the 2, the smallest number that 3 and 2 divide into is 6. We also need an x, and so the LCD is 6x. And so I'm going to multiply both sides of the equation by 6x over 1. So I multiply both sides by 6x over 1. I use the distributive property on the left side because there's an addition over there. And so you have 6x over 3 plus 6x over x equals 6x over 2. Right? Multiply every part of that equation by 6x. Simplify, so you get 2x plus 6 equals 3x. And you get this linear equation if you subtract 2x from both sides, you get 6 equals x. And boom, there's our solution to the problem. Remember that x represented how long it takes Candy to do this by herself. And so it takes Candy 6 hours working by herself, or working alone. Right? And again, it should make sense that in this case, the time that took Candy to do this by herself should be more than 2 for sure. And makes sense that it's more than 3 also, because Tina took 3 hours to do this by herself. Working with Candy, it takes 2 hours, so Candy didn't help her very much. So Candy must be slower at it. And so that makes sense what we got for the answer to the problem here. Okay, so that finishes what we are going to do with Chapter 8 altogether with rational expressions. So this finishes our discussion of rational expressions. Now remember that what we've talked about at the beginning, very beginning of the semester, Chapter 7 is all about polynomials. And so we talked about, in particular, what we did was we looked at factoring polynomials in particular, but it was all about polynomials. Chapter 8, all about rational expressions, fractions, algebraic fractions. And so now we've talked about, some basic things with rational expressions and how to work with rational expressions. Chapter 9, our next stop, is all about radicals, roots, fractional exponents. They're all connected together. When I say fractional exponents, I'm saying exponents that are fractions. And we want to look at how to simplify, how to work with those kinds of expressions. Very common to encounter roots and radicals whenever you're using algebra later on. So we want to look at how to kind of go about dealing with that kind of stuff. By the way, important in particular for college algebra is this fractional exponent stuff, because with fractional exponents, you've got to be pretty good at dealing with fractional exponents to deal with logarithms. And logarithms is an important topic in college algebra. It's an important topic in business calculus, in calculus. So exponential and logarithm functions, you have to be able to work with exponents that are fractions. And so an important chapter for college algebra, definitely. All right, so this is our goal now, is to deal with Chapter 9. So Chapter 9 is going to take us a little while to get through. There's a lot to do with radicals and roots and everything. So but it's going to be a huge change from what we've been talking about. Now, the way this author deals with, the way this textbook deals with radicals is that we're going to deal with square roots first and do a lot with square roots, and then we'll look at higher roots. So that means like cube roots and fourth roots and fifth roots, things like that later in the chapter. So for a while, all we're going to be dealing with is square roots. So remember that then that this symbol, when I write the square root of a down like this, right, that's how you read that, first of all, right, that's the square root of a. Technically, there is a number written right here in the radical that's a 2. We typically don't read that or write that 2 down. We do if it's a different number. That's called the index of the root. And so the index of a square root is 2. We just typically don't write the 2 down. It's the only radical where we do that, where we don't actually write down the index. All right, and the square root of a is defined to be equal to x, where first of all, x is greater than or equal to 0. The x has to be positive, and x squared is equal to a. So it's a number that when we square it, we get it's equal to a. X has to be positive. That's why it's sometimes called the principal square root, because it has to be positive. Also, what we know I'll talk about that in a minute. So there is a restriction on a, but we'll deal with that in a minute. So some of this, you should be no problems with this at all. So the square root of 36, you're looking for a number that when you square it, right, you get 36. And so the square root of 36 is equal to 6. Now, there are 2 numbers that you can square to get 36. 6 squared is equal to 36, and negative 6 squared is equal to 36. Notice that's why I had to put this restriction on here, is that the square root is defined to be the positive number, that when you square it, you get the value underneath the radical. And so it's got to be positive. So square root of 36 is not equal to negative 6. It's equal to 6. Right. Square root of 81 is equal to 9. Square root of 100 is equal to 10. Square root of 169 is equal to 13. You should know at least up through square root of 169 as far as the perfect roots like that, and be able to identify those.
Okay, so I have a question real quick.
Go for it.
So pretty much any number times itself, whether it's positive or negative, is going to end up being positive, correct?
Yes, that's true.
Okay, that's my only question.
Yeah, if you multiply a number by itself, it doesn't matter whether it's a positive number or a negative number, you're going to get a positive answer. And that's why, Xavier, 6 squared is 36, but negative 6 squared is also positive 36. Right? You always get a positive number. And that's why I have to put this restriction on here that x is greater than or equal to 0, that when we're talking about square roots with a radical symbol like that, it's only the positive one that you use. Right? So that's why the square root of 81 is not equal to negative 9. Even though negative 9 squared gives you 81, it's not the square root of 81. It's not what that radical symbol means. That radical only means you get the positive one. like that.
Okay.
Yeah, okay. Now, notice one thing that's going on here, and this is kind of sort of related to what your question just was. If you have a negative number underneath the square root like that, square root of negative 25. Now, we know that the square root of 25 is 5, like that, but the square root of negative 25, right, we are looking for a number that when you square it gives you negative 25. And Xavier, you just asked that question. But when we square a real number, we always get a positive answer. So, well, there is no real number where this would work, right? So there's no real number that makes this true, right? So there's no number I can put in there and square it and get a negative 25 because like you said, Xavier, a second ago, when you square a number, it doesn't matter whether it's positive or negative, you end up with a positive answer. So there's no way you could end up with a negative 25 as the answer. So if you have a negative number underneath the square root, what I want you to write at this point is not a real number. Notice I'm not saying that you can't do it. I'm not telling you to write it's not possible. I'm not telling you to write it doesn't exist. I'm just saying it's not a real number. It turns out that there is a number system where you can find the square root of negative 25 and write it down, called the complex number system. We're not quite ready to do that yet. Now, we are going to do that as intermediate algebra students, and college algebra students need to be able to deal with this. So there is a way to deal with the square root of negative 25, but just not in the real number system. So we'll actually look at a different number system at the end of the chapter and see how that works. For now, all I want you to do is when you see a negative number underneath there, I want you to write not a real number. All right? All right, a little bit with some things with arithmetic to deal with. So if you have the square root of 36 plus the square root of 64, like that. This is not, you do not take the square root of each one of those separately. This is not equal to, so I'm going to put not equal to 6 plus 8. Instead, what you have to do when the radical symbol is kind of like a grouping symbol, and so you have to do inside the grouping symbol first. So this is the square root of 100. You add them together first, and then you write that that's 10. Right, notice the other way, 6 plus 8 gives you 14. That doesn't work, right? So that's not true. So if you have an addition or subtraction problem, do the addition or subtraction problem first. Now, on the other hand, if you have the square root of 36 plus the square root of 64, that's different, right? The addition is not underneath the radical there, and there you would add or do each of those square roots first individually, write 6 plus 8, and then get 14 as the answer. Right, so there's a big difference between the addition being underneath the radical, so that's inside the grouping symbol, and the one that's not inside like that. All right, so wanted to kind of point that out. The next thing I want to talk about is, these are all perfect roots. If you had something that's not a perfect root, we're going to talk about simplifying these in a little while, but for now, let's just look at a number that's not a perfect root like the square root of 10, and let's say we want to approximate the square root of 10 just without a calculator. I would like you to be able to at least know what two numbers it's between. Right, and what do you have here? That 3 squared is 9, so 3 is too small. And 4 squared is 16, so 4 is too big. And so what do you have? What do you know about the square root of 10? It's between 3 and 4. Now that's all I'm talking about as far as approximating it. Tell me what two whole numbers that it's between. So if you wanted to approximate, let's say the square root of 60. Right, so what you want to do is pick one that gives you a number that's too small and a consecutive whole number that's too big. So what do we have here? That 7 squared is 49. So 7 is too small. Oops. And 8 squared is 64, too big. Right? So what do you know about the square root of 60? It's between 7 and 8. Right? It's got to be, it's a decimal number somewhere between 7 and 8. Okay, not a big deal, but I wanted to mention that. All right, so now let's look a little bit at variable quantities and square roots. So we want to look at the square root of x squared. Now you have to be really careful about an expression like this. I want to mention a couple of things here. First of all, you know, square root of x squared, well, if you had the square root of 3 squared, then that would be the square root of 9, which is 3. So what do we get here? That the square root of 3 squared is equal to 3. The square root of 7 squared would be the square root of 49, which would be 7. So what do we get? That the square root of 7 squared is equal to 7. And so what does it appear to be the case? It appears that the square root of a squared then should be equal to a. But that's not exactly right. And the reason why that's not exactly right is because that does not hold true for negative numbers. If you had the square root of negative 6 squared, see, don't think that you're taking the square root of a negative number there. Because what do you do first? You do the square first. So that's really the square root of 36, which is 6. And so what did you get here? That the square root of negative 6 squared is equal to positive 6. See, so it wasn't exactly like the positive ones, right? Square root of 3 squared was 3. Square root of 7 squared was 7. But the square root of negative 6 squared was not negative 6, but it was positive 6. It was the opposite of negative 6. Right? And that's going to be true anytime the number underneath the radical is negative. Square root of negative 10 quantity squared like that would be the square root of 100, or 10. So what do you get? That the square root of negative 10 squared is 10. And let me highlight that one too, because that's another example. And so what's true here? The square root of x squared is only equal to x. It's only equal to x if x is greater than or equal to 0. That x has to be positive, and then it's a true statement. If x is negative, then you get the opposite. And so sometimes you'll see this written like this, that the square root of x squared is equal to the absolute value of x. That way, if x was positive, the absolute value of a number is just itself. And if x is negative, then the absolute value gives you a positive answer, which is what you wanted. Now, I'm not going to try to make a huge big deal about this, but I do want to point out that what I'm going to do, rather than dealing with absolute values on these kinds of problems, what I'm going to do is make the assumption at the beginning on these problems that these variables represent positive numbers. So I will make the assumption that variables with square roots, that the variables are all positive. Well, I'll say represent positive numbers. Or technically, or 0. And that way we won't have to worry about the absolute value. So if we make that assumption, then we can say that the square root of y squared is equal to y. And the square root of z squared is equal to z. And the square root of x to the 6th power, so what if the exponent was not a 2, but something like that? Well, what are we squaring to get x to the 6th? What would we fit in there? Because remember, that's what a square root is. It's a number that when you square it, you get the number underneath the radical. So what would I square to get x to the 6th? I'm going to put a question mark there. And this would be x to the 3rd. And so the square root of x to the 6th is x to the 3rd. Square root of w to the 10th, then you're saying, what do you square to get w to the 10th? Right? And to fill that in so that you get w to the 10th, you put a w to the 5th in right there. And so this is w to the 5th. Notice one good thing here is that it's always half. So when you're taking a square root of a variable raised to a power, it's always half of the exponent. So that, if you know that ahead of time, that makes your problem a lot easier. So, for example, the square root of x to the 20th then would just be x to the 10th. Whoops. Square root of z to the 30th power would be z to the 15th. Right? It's always half when you're talking about square roots. Power is always half. The original power. So that's nice. If you know that relationship, then you can write those out pretty easily. Now, if we complicate this a little bit, if we say square root of 4 x to the 8th, for example. Well, then, because it's a multiplication problem, you simply take the square root of each of the factors separately, because you're saying, what do you square to get 4x to the 8th, right? And so you're looking, since you can use rules of exponents here, you're just looking at the square root of each factor separately. So the square root of 4 would be 2. Square root of x to the 8th would be x to the 4th. And so, again, we're making the assumption that the variables are positive here, remember. So you get 2x to the 4th. Right? So x is positive, always. X and z, in this case, are both positive. Right? We're making those assumptions at the beginning of these problems so that we can avoid having to deal with the absolute value stuff with these problems. The square root of 49z to the 12th. Then the square root of 49 would be 7. The square root of z to the 12th would be z to the 6th. Again, z has to be positive there. All right, do something that looks even more complicated, but still not a big deal. Square root of 121, a to the 10th, b to the 4th, c squared. So it looks complicated, but all you're doing is looking at each factor separately. This is actually not a hard problem at all. Square root of 121 would be 11. And then you just use this idea that the square roots of each of those powers of variables are just at half the power. So this would be a to the 5th, b squared, c, like that. So not too big a deal. And again, here the a, b, and c, we're considering all of those factors to be, or all those variables to represent positive numbers only. Okay, so should be pretty straightforward, I think. All right, so now for the last part of class here, all of these roots have all been perfect roots, right? And so what we want to do is look at look at simplifying some radicals where it's not a perfect square, right? These were all perfect squares that we looked at. So this is what I'm talking about. We know how to deal with the square root of 36. Whoops. Square root of 36, because the square root of 36 is 6. 36 was a perfect square. Right? 36 is a perfect square. But what about the square root of 32? And we can approximate it. I know that. That's not what I'm talking about doing. I'm talking about simplifying this. And 32 is not a perfect square. And the question is, how can we simplify something like this if it's not a perfect square? So you can't evaluate the radical. Now you can find a decimal approximation, like I said. Like square root of 32, we know is some number between 5 and 6. That's not what I'm talking about doing. I'm just talking about simplifying the radical, which means writing the radical so that the number underneath the radical is as small as you can make it. So this is the way I approach this kind of problem, is I simply break it up into two factors. And the two factors that you use here in this particular problem would be 16 and 2. Now, 32 breaks up several different ways, but 16 and 2 is what you want to use here. 16 is a perfect square. That you want one of the factors, you want one of the factors to be a perfect square. And notice the 16 is a perfect square in this case. All right. Now 8 and 4 would have worked also, but 4 is smaller than 16. You want the biggest one you can if at all possible. So how does this help you simplify it? Well, the square root of 16 times 2 then would be the square root of 16 times the square root of 2. We're using this property that the square root of a times the square root of b is equal to the square root of a times b. That you can multiply two square roots together. Now, there's one time when that doesn't work, but we'll talk about that later. But if a and b are both positive, that's always true. So square root of 16 times 2, so I'll just write if a is greater than or is equal to 0, b is greater than or equal to 0. So square root of 16 times 2 is equal to the square root of 16 times the square root of 2, and then just evaluate the square root of 16, and you get the 4 times the square root of 2. So this is considered the simplified form for the square root of 32. You're trying to write this so that the number underneath the radical is as small as you possibly can make it. So the square root of 32, we would simplify it as 4 times the square root of 2. All right? So what you have to do is practice this and practice how you go about breaking numbers up. So, for example, the square root of 27. So it takes a little bit of practice just figuring out how to break these factors up. So 27 is not a perfect square. So what are you doing here? You're looking for a factor of 27 that is a perfect square. And so that would be 9, right? Write this as the square root of 9 times the square root of 3. Well, actually, technically, let me not skip a step here. Technically, first of all, it's the square root of 9 times 3. And then that would be the square root of 9 times the square root of 3. And then the square root of 9 is actually 3. So this would be 3 times the square root of 3. And so we say that the square root of 27, the simplified form of the square root of 27 is 3 times the square root of 3. They're the same number, but 3 times the square root of 3 is considered the simplified form because the number underneath the radical is as small as you can make it. All right, so let's practice that a little bit more. So the square root of 50. So we're looking for a factor of 50 that is a perfect square. You know, so 10 and 5, you don't want to use 10 and 5, right? So don't use the square root of 10 times 5 because 10 and 5 are not perfect squares. 10 and 5 are not perfect squares. right? So don't use that one. Instead, what do you want to use? You want to use the square root of 25 times the square root of 2. Right? So square root of 25 times the square root of 2, 25 is a perfect square, so that's the one you want to use. And so what do we get here? That's 5 times the square root of 2. And so the square root of 50, its simplified version is 5 times the square root of 2. This takes practice, and in some cases, maybe the numbers are too big, and so you might want to simplify it in pieces, possibly. So, like, for example, let's say you have the square root of 800. Oh my gosh, square root of 800. And you go, oh my gosh, how am I going to break that up? So think about a factor. Even if you can't find the biggest one, think about any factor that's a perfect square that's a factor of 800. And what a lot of people come up with because of the 800 is that it breaks up using a 100, right? That this is the square root of 100 times 8. Now 100 is not the biggest one, but that's okay. We can still use that to help us. So break it up as 108, that's fine. So that would be the square root of 100 times the square root of 8. And that'd be 10 times the square root of 8. But what's the deal? Square root of 8 would simplify again. It would break down a second time. And so that would be the square root of 4 times 2. So that would be the square root of 4 times the square root of 2. Square root of 4 would be 2. And so you end up with 20 times the square root of 2. Now, there are other ways you can simplify that that particular square root of 800, but that would be one way you could do it. So notice we did that in pieces. So we first broke down 800 as 108, and then we broke down 8 as 4 and 2. And that eventually got us to 20 times the square root of 2. Now, somebody else might have looked at the square root of 800 and said, well, hey, I can break this up as the square root of 400 and the square root of 2. And then the square root of 400 is 20. And so you get 20 times the square root of 2. So that person did it in fewer steps, but if you don't see it, you don't see it. And so breaking it up in pieces is certainly an okay thing to do. All right, so now let's look at variables and how we simplify variables like this. Same thing. So, we know as long as x is positive, right, again, throw that in there, that x is positive, that the square root of x squared is equal to x. And the square root of x to the 4th is equal to x squared, and the square root of x to the 6th is x cubed, right? It's always half. Square root of x to the 8th is x to the 4th, right? Always half of the original power. Well, all of those powers are even, so what if you look at an odd one? So what about the square root of x cubed? Now you can use it, it's half of that, but we don't want to deal with fractional exponents yet. We don't want to worry about that at this point. So how can I simplify that radical? And so what you do is just use the same premise that we were using with constants on the previous screen. Break it up into two factors where one of them is a perfect square. So x cubed, we could break up as x squared and x, right? Because x squared times x is x cubed. And so then the square root of x, break this up as the square root of x squared times the square root of x. And then the square root of x squared is one that I know. That would be x times the square root of x. And so that would be considered the simplified version of the square root of x cubed, would be x times the square root of x. But that would be, they're the exact same expression, except one of them is considered simplified. It's a smaller number underneath the radical. All right, let's look at another example like that. So the square root of p to the 11th. Square root of p to the 11th. Now 11, You don't want to divide that by 2 because that would give you a fractional exponent. So we're trying to simplify the radical. So what do? We break that up into a multiplication problem. And you want to use the biggest power that you can that you do know the square root of. And so that would be p to the 10th. And so we break it up as the square root of p to the 10th times p. And so that would give me the square root of p to the 10th times the square root of p. And then the square root of p to the 10th is one that I know because I can take half of that exponent and I get a nice number. I get a nice whole number there, p to the 5th. And so that'd be p to the 5th times the square root of p. Right? And so that would be considered the simplified version of the square root of p to the 11th. Would be p to the 5th times the square root of p. Right? Notice what you're doing is you're always just, if you have an odd power like this, you're always just breaking off a power of 1, and you'll always be left with an even power, and that will always be the biggest one. So, it should be pretty straightforward how you do that. So, let's say we have the square root of 12 x to the 5th y to the 3rd. So do something a little bit more complicated now. So what we're going to do is we're going to go through each factor separately and break them up like we've just been talking about. So this is just a combination of all the things we've just been working on. So what about the 12? We could break that up. Remember, we need a perfect square. So that would be 4 and 3. Remember, don't use 6 and 2. I know it's true, but it doesn't help you to simplify, right? And the reason why, because neither 6 or 2 is a perfect square. So which one do you want to use instead? You want to use 4 and 3 because 4 is a perfect square. So that's the preferred one right here because that would allow you to simplify it. X to the 5th, just like we saw on the last screen, we'd break it up, take the biggest power out of x to the 5th that's even. And so that'd be x to the 4th times x. And y cubed, we'd break that up as y squared times y. And so then break this up into 2 radicals. This would be 4 x to the 4th y squared in the first radical. And in the second radical, I'd be left with 3xy. And that middle step there, gradually I'm going to start eliminating that middle step, probably. And then the square root of 4x to the 4th y squared would be 2x squared y. And then the square root of 3xy is what's left. That's the part that I can't simplify anymore. And so that expression would be considered the simplified version of the original one. Right? Our original one was square root of 12 x to the 5th y cubed. And so that's the simplified version of it. Now, it ain't a lot simpler. I understand that. It looks just as complicated, but it's considered simplified because the number underneath the radical is smaller. All right. Let's say, let's do another problem like that one. So you have several examples to look at. So you have the square root of 75, x to the 7th, y to the 8th, z to the 9th. So try to make it a little bit complicated here. All right, so what we're going to do is we're going to go ahead, I'm just going to go ahead and go to this step right here where we break it up into 2 radicals. And so how am I going to break up 75? What would be a factor of 75 that's a perfect root? Anybody want to tell me instead of me talking all the time?
I'll probably get this wrong.
Charlotte, what did you say?
25 times 3.
25 times 3. There you go, Charlotte. Thank you. And then x to the 7th, how am I going to break up x to the 7th?
I was going to say 6 and 1, but 6 isn't a square.
No, but it doesn't have to be a square. Remember, all you're doing is looking at what, when you're taking the square root of a power, you're just looking at taking half of the root, or half of the power. So x to the 6th is the one you want to use. Because you know that the square root of x to the 6th, whoops, let me write it over here. Square root of x to the 6th is x cubed. So you do know, you're just taking half the power to do that. Because remember, x cubed squared is x to the 6th. So it's the number that you square to get x to the 6th. So yeah, you want to use an even power. So x to the 6th is definitely the one you want to use. And then what about y to the 8th?
Y to the 8th would be 4 and 2.
See, you're making it more complicated than you need to here. Y 8 is already even though, isn't it? See,
Yes, sir.
since it's already even, you just bring all of it over here. I put that one in there deliberately to kind of throw you off a little bit.
And wouldn't Z be the same thing too?
See, z to the 9th, remember, it's half of the power. So half of 9 is 9 halves. We don't want to use 9. You remember, you're not taking the square root of 9. You're taking the square root of z to the 9th. So I heard somebody say 8 and 1. I'm not sure who said that. But that's exactly what you want to do, is you want to put z to the 8th and z like that, right? Because remember, what's the square root of x to the 6th is x cubed. What's the square root of y to the 8th? That's y to the 4th. Square root of z to the 8th, z to the 4th. You always just use half the exponent. So you're looking for an even exponent. The key here is with square roots is you want an even exponent. Those are the ones you know.
It's supposed to be Z to the 9th.
No, but what am I doing? I'm breaking z to the 9th up into z to the 8th and z, like that.
Oh, okay.
Right? And because what do you want to do? You want to get as big an even power as you can out of z to the 9th. So what's the biggest even power you can get out of z to the 9th? Well, that would be z to the 8th, right? Just like the biggest even power I could get from x to the 7th would be x to the 6th and x. And so what do you end up with here? 5 x cubed, right? You're using half the exponent. Y to the 4th, z to the 4th, times the square root of 3xz, like that. Remember, with powers of variables, you always want to use and get an even power, the biggest even power that you can get from the variable. So the square root of q to the 13th. What's the biggest even power I can get from q to the 13th?
12 and 1.
Yep, that's right. So this would be q to the 12th and q to the 1st. And then what's the square root of q to the 12th? You use half the exponent. It'd be q to the 6th. And then the square root of q just comes down for the ride like that. Right, so you always want the biggest even power that you can use when you're dealing with an odd power. If the power is already even, then you can simplify it just like it is. All right, let's see. Let me finish with one last problem, and then that will kind of shut it down for the day. We've done a lot of stuff here. So this is, by the way, I'm on. So this is section 9.2 in your book. This is page 1033 and 1034. Actually, this is page 1034 in this case. And this is problem number 130. You have a fraction underneath a radical, but there's no difference in how you deal with the problem. So don't freak out. Don't freak out on me now. All right? You have the square root of 72, x to the 5th over y to the 6th. First thing is you take advantage. Multiplication and division are exactly the same with radicals. You can take two radicals and you can multiply them. You can also take them and divide them. Right? These properties are the same. So in other words, what I can do here is I can just break this up into two square roots. The square root of 72, x to the 5th, over the square root of y to the 6th. So do that, break them up into two separate square roots, and then go ahead and simplify each one of them separately. So the square root of y to the 6th in the denominator would be y cubed, right? You find half the exponent. And in the numerator, the 72x to the 5th, this is one where I'd want to break it up. So the 72, the factors I would use for 72, anybody want to guess? Or don't guess, hopefully you know. What I'm looking for.
8 and 9.
So you don't, okay, 8 and 9 is okay. That's not a problem, because 9 is a perfect square, but I can do better than 9. What would be a factor of 72 that's bigger, that's a perfect square?
36.
36, there you go. Very good. So this would be 36 and 2. 8 and 9 would work. It'll just take you an extra step to simplify it. That's okay. And then x to the 5th, this is what we've just been discussing. It's an odd power, so you want to break it up into the biggest even power. So I'd use x to the 4th and x. And then the square root of 36x to the 4th would be 6x squared. The square root of 2x just comes down for the ride. And then you have y cubed in the denominator like that. Right, so you first break it up into a numerator and denominator like that. And then you simplify each one of them separately, like I did right there. And then see what you've got left at the end. I tell you what, before we leave, let's work one more problem like that. I think that would be good to work another example like that. So let's do something that's similar to that. Let's say we have the square root of 40 x to the 9th y cubed over 16, let's see, let's use different letters there, 16 w to the 6th z to the 10th. Now it looks horrible, I understand that, but this is not really, ends up not being a hard problem to simplify if you just do this step by step. First of all, write it as the square root of the numerator over the square root of the denominator. And now just treat it as two separate problems. Now in the denominator, I know the square root of 16 w to the 6th z to the 10th. The square root of 16 would be 4. The square root of w to the 6th would be, remember it's half the exponent, so this would be w cubed. Right, the exponent's even, so I already know the root there. And the square root of z to the 10th would be z to the 5th. I already know that root. All right, and in the numerator, that's one where I have to split it up. All right, so I want you guys to help me. What about the square root of 40? How would I break up the square root of 40? Jose, go ahead.
5 and 8.
Okay, 5 and 8 you don't want to use because 5 and 8 doesn't give you 40. I understand that. But 5 and 8 are not perfect squares. Right? You remember, you want a perfect square that gives you 40. So what would be a better breakup for 40?
10 and 4.
There you
10
go.
and 4.
That's right. That's right. 4 and 10 is the one you want because 4 is a perfect square. Right? So that's the one you want to choose here. Right? Always use a factorization that has a perfect square. And if there are no perfect squares, then it doesn't simplify. Right? So, you know, like the square root of 30, think about the square root of 30. The only factors for 30 are 6 and 5 and 3 and 10 and 2 and 15. Well, there's a bunch of them. None of them are perfect squares. And so the square root of 30 doesn't simplify. Right? That's already simplified. All right, x to the 9th, I'm going to break up as x to the 8th and x. Right? We use the biggest even power you can get. And y cubed I break up as y squared and y. And so I'm left with 2x to the fourth y for that radical, right? That's the radical I'm evaluating. And then the square root of 10xy just comes down like it is. And this would be over 4w cubed z to the fifth, like that. Now, as it turns out in this problem, there is a common factor of 2 and 4, so I can actually reduce the fraction at the end. So you want to do that also, so don't overlook that. So you end up with x to the fourth y times the square root of 10xy, all divided by 2w cubed z to the fifth. That's easy to overlook at the end. So now I know it looks horrible, but just take your time going through these problems, practice that. And if you kind of break it up into these little pieces, you'll find that it's not going to be too bad. So, anybody have any questions on that last problem?
No, sir.
No, sir.
Okay. So I do want to give you some textbook homework to look at, to practice. Remember, you have WebAssign homework. We talked about that at the beginning of lecture today. So look at the WebAssign homework for sure. But practice on word problems. If I can find it real quick here. These are on page 990. So on word problems, if you're looking for more word problems to do besides what's on WebAssign, this is on page 990, and this is problems 447 through 457 odd. There's 5 problems in there that would be great practice problems for the test. And then we went into chapter 9 after that and started simplifying radicals. So 9.1, this is page 1021. And really, you can do any of the problems from problems 1 through 45 odd. Those are all great practice problems. And then section 9.2, this is on page 1033. Again, any of those problems, and now I'm going to write this down, but just 1 through 139. Now, I know that's I'm sorry, not 1 through 139. It's 53 through 139. Still a lot of problems, and I'm not expecting you to do all of those problems, but those would be great practice problems. So I'm just going to say great practice right here. All right, so remember that I've got your exams. I'm going to be grading those, working on those over the weekend. I hope to finish them by mid to late next week. I will be emailing you that I'm posting the grades on WebAssign. You'll have a WebAssign gradebook that you have access to. And when you go to the WebAssign gradebook, the exam grade will actually be on there. If you want the graded exam sent back to you, I will email it to you. You just have to email me, and I'll respond back to your email, and I'll send you back the graded copy of the exam. And I think that's it. And so anybody have any questions?
I'm good.
No questions.
All right.
Good over here.
All right, Justin, I just need you to hang on just for a second. And everybody else, I will see you. Remember, I have office hours on Sunday, Monday, Tuesday, Wednesday nights. So take advantage of those office hours. Come by for help. If not, hopefully I'll see you at live lecture next Tuesday. Have a great weekend. And try to get some algebra done. Remember, your WebAssign homework is due on the 9th. So you have Chapter 8 WebAssign homework due October the 9th.